Okay. All right. So thanks for coming, guys. I'm Longfei Shangguan, previous senior researcher at Microsoft Research, and now assistant professor at the University of Pittsburgh. So it's my great honor to introduce our plenary talk by Dr. Yiran Chen. So Dr. Yiran Chen is actually currently a distinguished professor at Duke University, and he's actually, the head of the Athena, right? It's an AI initiative by NSF. And also, like Dr. Chen, we have a lot of awards in the past few years from both actually ECM and his ECM fellow, and Triple AS fellow. So without further ado, some time.
Thank you. Thank you very much, Longfei, for the introduction. It's my great honor to be here, to give the talk. I remember the last speaker said, the worst slot was the one before the lunch, and the second worst one was this one. So I took that one. It's my honor. Okay. Sure. The title of my talk today is, unleashing the potential of the edge computing with AI hardware and software innovation. So we're trying to summarize what we have done in the last couple of years. So before, let me see. Okay. So before we start, let's give a short introduction about our AI Institute, which is a $20 million effort sponsored by both National Science Foundation, thank you so much, and also the Department of Homeland Security. So these are our perspective regarding the edge computing. So in a conventional view, you're basically going to view the whole edge computing in 3 different layers. You're going to have the data center, the big cloud I will show here, and then you have the connectivity layers going to connect the edge devices with a cloud, and also you have the edge devices. There's a lot of variety about different devices you're going to use. So it can be very difficult, for the cross-layer optimization, because you realize there are 2 layers about the computing and 1 layer about the connections. And traditionally, for the connectivity and the computing, they are belonging to the different society, right? They actually rarely talk to each other. Sorry to say this, but yeah. And also the computational and the communication are considered individually. So when we proposed this AI Institute about 3 years ago, we thought we should review the whole thing the different way, which is a computing perspective. I'm not saying the communication is not important. I'm just trying to convert the communication or the connectivity to the compute part of the computing. So the compute nodes are defined by the local computing, which is the edge device, and the collaborative computing, which include those devices, and also communications between those devices. And also compute and data connectivity, which more represent to the connections. And also the data protection, because we believe the sharing and the collaborative learning across the whole devices will require such protection for the data and also for the model we'll show you later. So we're trying to develop a unified compute-centric view of the edge computing space. So we're going to enable both a vertical, which means across the layer, and a horizontal with across the nodes in optimization to address the heterogeneities between the devices and also the data. So of course, AI going to play a very important role. Everybody can, can view, and also to define and execute those strategies. So basically our goal is trying to build a highly scalable, efficient, and robust, which also means secure edge computing system powered by the AI. So this is let me see, can we remove the how to hide this? Huh? It doesn't work. Let me see if there's any other way to do it. No, that's the only way. Are you mirroring your screen or you're not sharing your? I can press the button if it. Good question. Let me see. Maybe I should use this one. Oh, okay, here we go. Cool. Okay, so this is a geographical distribution of the Athena, which is the name of our AI institute. You can see we have 8, institutions joining this effort, plus, the 5 industrial partners and also a few community and educational partners that we show here. I'm not going through the details because you can easily access our webpage like athena.duke.edu, for all the information. Okay, so now it's not a problem to page it down. Okay. So if you look at how we are able to build up the AI design on the edge, they're actually called for multiple layers efforts. Now we're very familiar with, for example, the computer architecture and the software a solution stack, which are the core focuses of CTF from National Science Foundation, together with a hardware software co-design. But we also needed to design basically hardware or the circuit, to run those machine learning models. We'll show a little bit of the example later on. And in the very low level, we also understand there are some actors, from material and device. They're trying to develop the new material and device to represent, more advanced behaviors of these AI models or orthographers. There are a couple of challenges here. So number one, the resource. We do need a lot of resource, to play those models on the edge. And if you look at the growing size of AI models on the edge computing device, and we show here, following the publication data, you will see, we actually keep increasing the size of the AI model running on the edge, also on the cloud. Remember, the vertical is actually the number of parameters, but it's a log sum. Okay, scale. So the co-design of the model and the software and hardware to optimize the throughput and the memory became very important in the HD. Not even talk about how can use for different, the design space or something first. And the second one is regarding the task of personalization on the edge. When people are familiar with training the data, trying to deploy, the model on the edge, by assuming we don't need to add anything, which is wrong. Because when we are deploying the federated learning or any other edge model on the edge, like a domain-specific instructions, emotional tones and the culture factors, all those things require us to re-personalize the model on the edge for the different application, even for different data, or even for the different user or for different devices. So they become a must, and at the same time also become very complicated. There's some example. Let's say the task of brainstorming. You say, hey, why model is bad for the human? You say, in response, we are always, engaged on the phone with which is not good. That's one possible example. But in another example, you have large language model. I'm gonna say the summarization. You give some context, you ask some questions, and you give some result to summarize this. And you even have some open questions, and you're trying to come up with something new. It's relevant to the generative AI. So in the multilingual application, there's a very popular example for the large language model. The fairness across the languages, especially for the language with fewer data samples, I'm going to show later on, is essential but very hard to achieve. for the personalization. The third one is regarding the deployment of privacy and security. We all understand this. Remember I talked to one of our speakers about how to access the data, which is a very key question of the deployment of this AI models. So every device hold private data and conduct sensitive tasks all the time. Okay, so it's going to be very challenging, to prevent the privacy leakage from this IoT devices. And people try many approaches to protect this, and we'll show you later on, but still going to be generate a lot of the challenges and issues here. And also multi-device, edge computing scenario, like federated learning, distributed learning, collaborative learning. So on the first, allow the malicious devices. It's very easy to have one or two such devices across the thousands or even millions of those devices to conduct adversarial attack and poisoning attack, all kind of stuff. Bring challenges of ensuring the security of the system. Okay, there's one example to show you have cloud servers in which you're going to receive some data from the device, and you train the model. If you deploy, that won't work because you're going to expose the raw data to the server, which will be very difficult to protect, not just from the server side, also from the transmission side. Okay, we'll talk about the following topics. The number one is regarding the efficient AI training and the inference on edge. We try to give you people very high level introductions about what we have done without giving too much details. However, you are very welcome to read our papers and publish here and there, for all the details. So we'll talk about the design space exploration and talk about the hardware software co-designs, regarding the AI models. The first one is about the design space for the edge AI. So when we are designing the AI models, it's not like people thought, we just design the model and then we think about how we're going to apply to the model, because you need to start from very beginning to think about how you are able to optimize the AI model by considering the scenario you're going to apply, including the data, including the device, including all the constraints you may have. So this included that, for example, you want to design some efficiency-driven design, which means you want to consume the minimal resources. And you need to handle the efficient dense connectivity between the different levels of the features, because you understand the spots on the connectivity will create a lot of issues when you're trying to deploy the model on the device. And you have efficient building operator, because some operator may not be efficiently supported by the edge device. One example is we're working with Qualcomm using their Snapdragon, DISP microprocessor running on the AI models. They have some power, can run some operator very efficiently, but for some others, it would be very inefficiently. What are you going to do with this? You need to make some trade-off on this. And also efficient autonomy levels architecture design space with a minimal human per hour, because you don't want to get too much the labor involved, and especially those human instruments are very expensive. You can guess how much you're going to pay for one AI engineer, right? If you want to deploy one people for one model or one application, you simply will not be able to afford it. So people come up with some solution for the neural architecture search. It's very simple. You have the library of all the operators, so you have all the topological design, and you just follow some strategy to automatically design the models by taking the samples from those library components and to see which combination will give you the best solution in terms of the performance, in terms of efficiency, or even for the memory footprint. So one example is the visual recognition search, which we demonstrated last year in the AutoML conference. This paper was one of one of the 2 to 3 papers received the highest score. I believe not at least one of another one from U group. Yeah, it's like a average 4.5 or 5. I forgot. Okay, so I still remember that. Okay, so but one example I want to show here is there's one example to show you have the model have multiple branches. The reason you have multiple branches because each branch will be able to handle the objective with the different sizes, with very small one to a very large one. And traditionally, people need to hand wire those branches and make sure you are able to generate the overall performance, which can be benefit to all these models, or those are all this sizes. But neural architecture search, or the NUS, can actually automatically search all the connectivities, possible connectivities between different branches that give you the best solution. It will be much better than the human designing one. I will show here. This is a final result of one computation. We use this model in I believe for CVPR for some applications. Our model ranked number one this computations by simply search for the best solution. And we found out there are some topologies we search can never be actually discovered by human using this. Of course, I'm not even talking about this our result, it's about or any other solution, blah, blah, blah. But this is one example to show how this automated process will be able to benefit us. So you can also apply the same technology on the autonomous driving. This one example, say you have a LiDAR to generate the point cloud, the 3D point cloud, and you are able to develop different operators so we can run efficiently and add into the library. And also here, this based on the higher order interactions. So you basically consider the different points, and for this the point wise or this is called the column wise, but you will be able to find out the different orders of interactions. It can be very adjacent, the point, this will be very far one. So you are able to handle this complexity for the interactions of all this point. And later on, you're able to generate another point operator, which would be the higher order interactions with the 2 1 plus 1 linear layers. So we are able to search for the best solution by varying the depths, expansion, the width, and so on and so forth. So the details are not that important, but the one important takeaway from here is, you actually can customize, the operators and also, the topologies, for the different applications by leveraging your domain knowledge and putting it into this, the library of the NUS and to improve the performance. This paper was published early this year. So this is another example for the recommender system. This would be the system you use every day. Okay, when you are using the web browser, you're trying to search for the different web page, they can predict what it's going to do for the next, and they can push the advertisement or the next page to you, even you are not aware of. So we work with Manta on these things, and the difference between this recommender system and a conventional CNN is you need to handle the various spots, embedding system, and also some and also very large the search space of the neural network, which was not traditionally handled by the NUS. So people use a weight sharing one-shot NUS, which is a very popular NUS approach to search different candidates for the best neural network. But you also need to define the different sampling approach to maximize the coverage of your search space, like a single operator, any connections. You have one operator, but you're able to handle all the sampling across the different connections. Or you have an operator balancing the dot product. Well, I'm not going to go through all the details, but those strategy will be able to minimize the sampling across all the search space and maximize the coverage of the candidate, the neural network, so that you are able to find out, the best neural network across all these candidates. And by doing so, you can dramatically reduce the size of the recommender system. And now we're working on with Qualcomm, trying to deploy this recommender system, which is usually running on the cloud to use on your cell phone. So you are able to run the recommender system on the cell phone that provides the better user assurance and a faster response time, for the different applications. And there's some common tricks which you are familiar with. One example is sparsity, because we all understand that neural networks are very sparse. When we say sparse, this basically means, the neural network has a lot of width, the value of which are close to 0, which is good. Why? Because you have an input times by 0, the output will be 0. You don't need to compute them, right? But traditionally, if we just do it, we say we just skip the computation with something times by 0, you will generate what? You will generate a lot of cache misses, because you basically bypass some data stored in the memory, and you're going to find somewhere else which may not even be preloaded into a cache. So what you should do is actually you're going to prune the neural network, which means you're going to get rid of those close to 0 width or the parameters in our structural way, so that can still preserve the cache locality in your basically edge devices, so that you don't really generate a lot of cache misses. Okay, because everything could be random, you're trying to minimize the randomness in this. So this is something called the structural pruning, which was a technique we proposed in 2016. That's a long time ago, actually. If you consider, the faster paces of the AI research, but this paper has been cited by more than 2,400 times. Simply because it's a very simple trick that makes the execution of the AI model much more efficient. And you can do, for example, how you can find out this, the structural relationship. You can actually remove the width, corresponding to the whole kernel, to the whole layers, for the whole kernel, or even for, the same position, the different kernels, because they going to represent the data either horizontally or vertically. So you can still preserve this cache locality. And you can apply the technique not just for the CNN, for RNN, for all kinds of neural network. It actually has been the standard processing strategy for all these AI models. You can do even more aggressive. You can actually really consider the bit levels of bars. What does that mean? Think about this. Traditionally, when you do the quantization, you say have an 8-bit. Now you want to quantize the model to 4-bit. You're going to either do it, you truncate the first 4-bit or the last 4-bit. Who tells you this? Who tells you can only do this? You can truncate, the column are the number 1, the number 3, the number 5, and the number 7. You can do it. But the issue is how you can identify why I can do this, right? Because the bit will distribute totally completely randomly in your memory. But by using the structural pruning, you actually can consider the bit will be the weight in the neural network and prune the bit in the structural way. And by doing so, you can randomly prune any single columns and still be able to preserve the same number of the quantized bit. So that's one advantage of doing this. So that's something we proposed two years ago. Yeah, I'm not going to all the details, but too detail talk about how you can do this, group last, so blah blah. So, but you don't need to know all the technical details. So it basically gives you the example saying, you have the hardware and software code design. Okay, you need to understand how hardware going to work. The cache misses, the number of the bits you can store on the memory. What are the hardwares you have? Which operators in this hardware can operate very efficiently, so on first. And you have all these informations, and the next thing you can do is you actually apply the knowledge of all this to your AI model design to make sure the AI model can perfectly align with the characteristic of the hardware which you can run on it. So this is ideas. Not even talk about the compiler optimization, but we'll show you later. So you have many other, advanced applications. One example is you can take GAN, generative reinforcement network. There are 2 engines, right? Discriminator or generators. So you can design a separately. You can say have two pipelines, one for generator, one for the discriminators. Or if you look at the pipeline, the many components are actually shared by those two pipelines. You don't need to redo it. The only thing you do is you give the different, tag at the end, to show the different, the compute the different loss. So if you can really share all these hardware, you can dramatically improve the efficiency by more than 10 times. No kidding, because there are a lot of data movement between different entities. You can completely remove it. And also, if you look at the generative AI, you start with some noise, and then you start to generate all this output, the contents on the first. When you start doing it, you need to insert a lot of zeros in this initial vectors, and then you gradually grow everything to be very, very big. Remember, 0 times anything will be 0. So don't do it. What you can do is you actually times non-zero stuff first, and you insert the product of a 0 into it. You can dramatically improve performance, right? Very, very simple trick. So this is one example to show, how you're able to combine this model optimization with Howard's, which was published 2 years ago from my group. So the best idea is, do we really need to have, so much information about the AI model to compute it? Or in other words, can we approximate, computation of the AI models will dramatically reduce the computation? Remember, it's a very, very simple trick. You must learn like SVD decompositions on the first. You start with a matrix and some eigenvalues and some matrix, you times them together. And the only thing you need to compute is just something in the middle, right? And you actually can really decompose the matrix with the linear combination of the product between the coefficient and some basis. And you just compute the basis with something and add them together. You can do this. You're basically going to have a lot of bases and times a lot of stuff, which is basically will be the same. Right? Comes a different input and then add them together. And you can also design the hardware to accelerate the whole process with very minimal loss of the accuracy, but dramatically improve the performance. And you can even do more than that because the bases are the same. There are a lot of computation. You can see them again and again. So what you do is you can store or cache this intermediate result. You don't need to recompute them in a redundant way. And by doing so, you can improve the performance, by more than 2 times, and also reduce the energy efficiency more than 3 times because you just store some values which can be reused later on. When you think about how you can improve the neural network, I think about how you can propagate these values from beginning to the end. We're going to have you have the input. You times by something, you get some result, right? But a lot of zeros in the middle, you compute them in a redundant way. You say, okay, I'm going to remove it. But later on, they come back again. The input come back again, and then you do recompute everything. Wait a second. Why I want to recompute the same input again and again? Even we already know the data flow of the AI models. We should not do it. Actually, we should somehow design the whole data flow and the AI models, or basically a kernel, such that when we load the input will be used just once, and we compute all the outputs which going to use this input, and then we retire this input. We never load them back. By doing so, we basically remove this redundant, loading, unloading stuff, actually remove this. So we work with AMD research on this. We're basically saying we can really do the pruning on the neural network so that if we know there's an input, compute with something, the input will be used by all the components which require the input and retire. And later on, this input never come back. And there's a black one show here. Okay, so this be one example. But we of course need to compile, this AI models and prune the neural network and make sure this AI, basically this input never come back or from the first. So now let's talk about another thing regarding the personalization. So personalization is actually a very popular approach, and it will be necessary approach, I will say. because each user have very unique demand for the AI, and we need to somehow customize our model to adapt this. So the feasibility of the personalization is also approved. For example, the large language model showcases remarkable multitasking ability as a personal assistant. But for each people, they have a different behaviors, which we need to adapt to. And the successful deployment, of the large language model in the vertical applications such as law and also healthcare require us to retrain or fine-tune the models. And then people show it. Nobody really going to train the model from the scratch. They only have a pre-trained model and then customize this. So there are a couple challenges on this personalization. It's very similar to the generic, challenges, like, insufficient personalized data. It's very common because what you have compared with the pre-trained model may be very minimal. And also the inadequate, computational resources. Because in many cases, when you deploy the model, you actually deploy it to the edge devices or some other device which do not have, 10,000 GPUs, and you have a privacy concern. You don't want to expose your training data to whoever can access this. Okay, so let's talk about accessing data in sufficiency. One solution people came up with is a federated learning, trying to enable the collaborative learning, leveraging more data while ensuring the privacy. You have all this kind of scenarios, and you're trying to somehow provide your input, by the different devices and also train the model. We actually have one paper recently talk about this, particularly in the large language model called the federated instruction tuning. Remember, the tuning of the large language model includes many components. One important one is the instruction tuning. You provide the instructions, and you give the large language model the feedback. Traditionally, you can only do this, on one machine or so on first. But now, you may be able to allow different people to train the model in the different devices, and they can consolidate, in the centralized server of doing this. This result basically show that, if we have the centralized model, you have, the accuracy will be the 81% of the GPT-4, and Llama, has a 67% of the accuracy GPT-4 can approach. If we only have the local 1, local 2, local 3, you may end up with this instruction training. You may end up with the input accuracy like a 71 to 72%. But if we add them together, we say, hey, those are 3 users will be able to train this large language model in the federated learning framework. You actually can bump up the accuracy at least by 76% of the GPT-4 accuracy. So of course, if you have more data, you can continue to improve it. So to give you the opportunity that you are able to leverage the talents of multiple users to train the larger language model without sacrificing the privacy. This is just one example. So, but there are many other ways to do it. Actually, for the resource insufficiency for the large language model, or for some other large model running on the edge. One example is the parameter efficient, fine-tuning method. You only train a small set of the parameter, which might be a subset of the existing large language model parameter or a set of newly added parameter. In other words, you're not trying to train the whole large models. You're just trying to train something which is a subset of the data or the parameters you're trying to train. The LoRa is always is one. So, and also the fixed tuning, you basically add something at the beginning, for the input, and want to make sure this can represent, the training and the promote training, tuning, what they are, and adapters, so on and so forth. So there's some paper talk about those, so we don't need to repeat this. But one example, we proposed recently is about the knowledge distillation. So the idea is, a lot of people talk about the distillation of large language model, right? So whenever you have, GPT-4, someone say, oh, you know what, I can train the teacher, the students, the training framework to learn something, distillate from this model. Yeah, and this actually give you the similar performance, whether, something else. But usually you sacrifice the generality of these models. And more importantly, if you really deploy these models, to the real scenarios, you basically start to see the drop to accuracy for very generic, scenario, not for the test case they give to you. Instead, you want to try, the test case that you collected, you will know it. Okay. So the knowledge distillation, which we propose, can significantly reduce the computational resources required for deploying this large language model. So what we did for following. So when we are training this distillation model, basically a student model, we also record the embedding information of this knowledge base. And when we record this knowledge base, and when we do the testing or the inference, in addition to the in addition to the student model classification, we also check the embedding between this input data with this knowledge base to see this, to check the similarity. And this embedding information will be used, to fine-tune our output so that we can improve the performance. So you can roughly understand the whole process like this. When you are doing the distillation, you're trying to capture the most important information of the original model and also the function analysis. But you're still missing some information which is associated with the training data side, which is also important. And this guidance can be somehow preserved by using our knowledge base we generated. So when we're doing inference, in addition to the distillated model, this embedding relationship will also help us to fine-tune the result and get output. In the traditional pipeline, which was mentioned in the talk before the launch, when we're doing the training, we have a training data side, a validation data side, a testing data side. After training and validation, we just use the testing data to get the result. But the additional knowledge we abandoned in the training data side can be reused in the inference. That is the trick we play here. Not the validation data side. Okay, that's the difference. So, and by doing so, we can dramatically improve, the performance of the distillated model. And we need to pay a little bit performance overhead here. It's about 5%, on top of the original inference time, and a little bit, the memory footprint. But we can dramatically improve the deployment and the accuracy of the distillated large language model. Okay, we have about 10 minutes to talk about the privacy. So. This is a chart to show the Edge Cloud collaborative learning framework. You have to add the device, so they don't want to upload their data to the server, and so they want to preserve the data and the prediction of privacy. And they just give the feature to the cloud server, and the cloud server, they don't distribute their model to the user. So they actually only give the result, to the edge, so that the edge device will receive, the output from the cloud server. And so be very safe, right? You don't send the data, or you send the feature, and then based on the feature, cloud server will get the result and send back to the edge device. However, it's been very slow and very inefficient. So most people are going to say, okay, what I'm going to do is, even we are doing, sending the feature from the edge device, to the cloud server, we are still expose some information outside the edge device, and people can leverage this. For example, the input of the cloud server's model do this the property inference and also the model inversion. And also for the output, of this cloud server model, you can get a prediction inference. So all this security concerns are real because when you are exposing the features of the data, all the output of the models, those output or the features have already carried some unique properties of the data or the model. So what should we do here? So we propose a defense method called scissors. So which is systematically addresses the privacy leakage in the collaborative inference for both data leakage and prediction leakage. So what we do here is we have 3 goals here rather than only 2. Originally we have 2 goals. One is the prediction. Okay. So originally have 1 goal, which is the prediction. You want to input the prediction accuracy of the model as high as you can. But now we're adding 2 new goals. One is the data protection. You're trying to use the minimize the mutual information loss so that you make sure data protection will reach some threshold. And also you have a prediction protection, which is another goal. So the whole optimization goal becomes 3. We're trying to maximize the prediction accuracy and minimize the data protection and the prediction protection rate. So, and by doing so, you are able to train everything by simultaneously do the min-max optimization on those 3 goals and find the final result. There is a trade-off between those 3 goals, but that could be the best trade-off we can make. So, and also there are some other concern regarding the IP protection of the cross-silo scenario. There's one example identified by one paper published 4 years ago. You have a bank. Bank, records the users' revenue and expenditures on the first, and you have an e-commerce, which they have the users' browsing and the purchasing, histories, and they trying to work together, to train a model we can mutually benefit both. However, if they share the data in between, which is a vertical federated learning to show here, you basically one party, no matter going to be the bank or be the e-commerce company, they actually can probe another side to gather information which were not belonging to them. For example, they can actually find out using the representation to really find out users purchasing history from the e-commerce company, and the company can actually try to steal the user statement of the credit rating by exploring the gradients of the model they're going to send. Okay, you try to prevent people from doing this. So again, so what you can do is you have 2 goals here. One goal is to preserve the performance of this vertical federated learning. The loss of the prediction should be minimized. So that'd be the one goal saying you're trying to improve the performance. Another one is to reduce the IP leakage of the labels from the representation, since the party tools of representation content as less information as possible about what are they trying to protect. This became another min-max game you have to deal with, rather than you have only one game at the very beginning. So now you're trying to maximize the performance of the vertical federated learning framework and minimize the mutual information you're trying to lack to another parties. So this one paper was submitted to this year ICCB. So, but I will say, actually, there's a security concerns about this neural network or federated learning are much more than that. And unfortunately, we need to deal with another issues, which is called the transferability. Transferability can be good or bad. The good thing is, if you are designing, one neural network which is good, on one data side, it's very likely this neural network will be working well on another data side by fine-tuning a little bit or add some layers, which is a good transferability. The bad transferability is like this. If we can somehow draft a text on one model which running very efficiently. This attack model will actually attack another model on the same data set also efficiently. That's the best transferability. So we had a couple papers a couple of years ago talk about this. We say, even we don't really know, the model trying to protect, but we are able to draft another model which shows the similar performance on the model on the same data side. We actually can draft a very efficient attack on the model you're trying to protect. But there are multiple ways to do it when you identify the sensitivity layers, sensitive layers, and drop the the attack model, blah, blah, blah. There are more details, you can read our papers. So one efficient way is, to apply the adversarial training on the neural network. So make sure when we are training the neural network, the neural network has been trained in the scenario which we don't want, right? So, and by doing so, we can naturally give the models some immunity to this attack. But the issue is adversarial training is very costly because you need to generate adversarial samples and train the models. And even for 20 and another downside is if you have only a small number of the devices in the federated learning has been adversarially trained, that won't really help much. One example here is if you have 100% of all the clients, all the devices, models have been adversarially trained, you can have, the natural accuracy 78% down to 67% adversarial accuracy. But if you only have a 20% device that has been adversarial trained, that really won't help much, especially when you're increasing the complexity of the data side. You start to see this protection capability will dramatically reduce down to like a 19% accurate, basically it's a random guess. So this becomes a very significant issue, for the federated learning to be against to this adversarial attack. Because you basically need to train most of the edge devices in the adversarial way, which would be very costly to achieve, reasonably good resilience to this attack, adversarial attack. So the good thing is you don't have to train all the devices in the same way, because we already handle the very large heterogeneities of the devices in the federated learning framework. You may start with, the camera, the sensor, which have very minimal, capability in terms of the computational resources. To the handheld, device, to the laptop, you can apply only the part of the neural network which you design it on the different devices, and we show here. And depends on, the computing resources availability, you can apply the different component, which we carefully drafted so that you can still train them in a collaborative way to get, the unified, the model, but then you can truncate the model for the different component that then deploy to the different devices with different requirement. And we show here. And by doing so, you probably only need to train very few devices, with, other adversarial training or something first, so I can still be able to protect, the robustness of this model and also minimize, the computational cost. Okay, so I think I can conclude my talk. So I talked about a lot of examples regarding the hardware design, the algorithm design, even for the system design, regarding how we can collaboratively train the models. So, but if you look at, the large language model, which is a very hot topic now, and especially people trying to deploy the large language model on the edge device, there's still many challenges, and some of them became even more severe, okay, than the conventional deep neural network model on those devices, and we still need to handle it, especially if they have a limited, the computational resources. There's some technology we can deal with in the future. We haven't done yet, like the cheating scaling rule, instructions following step-by-step reasoning, those applications prompt engineering, which is very different from the training process which we have been dealing with, and also some training and alignment tuning so on first. Those new way, to train the model and to use the model give us the more opportunities, to conduct the research under in the edge computing context. So that will become the future research direction we're going to follow. Okay, I think I'm going to stop here and open for any questions you may have. Thank you.
Questions?
Yeah.
Well, I have.
Sure.
So if you look at the edge computing,
Yeah.
if you look at the edge computing in Google Cloud, right? So they're deploying Anthos and deploying all of machine power using the latest GDC Global Distributed Cloud and putting all of firepower on the edge and incorporating many of these potential things. And also there are potential GPUs that can be put in the CPU. So how does that relate to the shortage of resources and the things that you described? There isn't a lot of machine power on the edge and all of that, right? So these are two different views. You describe a view where the resources are limited. Google, on the other hand, is coming up with a model that says, I can take all these machines and deploy them with 5G RAN type of networks. And you pretty much have almost a mini data center at the edge that Google is deploying across many of these cities that we see. So if you can just compare the two, and what does that really mean for the research that we're doing where the resources are limited versus a model that says we can add our resources here?
Okay, it's a very good question. So people keep deploying more resources on almost every single layers on edge computing, starting from the cloud for the so-called edge data center and to the edge devices. So I will say in the history of the consumer electronics, there's never a time we say we have sufficient computing resources. Never. Whenever you have another new generation of devices or the computers, people will quickly use up or whatever you can to provide. That's number one. Number two, when we're trying to offload all these applications to the cloud, to the edge data center, so the limitation in many cases do not come from the equipped computing resources on the cloud or on the edge data center. It's more like from the bandwidth or the latency. Because think about this. Let's say we're talking about driving car. Okay, in many cases, you need to make decision in very short time, let's say a couple of milliseconds. But if we're just trying to upload some data to the cloud center and come back, let's say from here to Seattle or somewhere, at least you'll need to wait for 200 milliseconds simply because the distance between here and also Seattle. You have to rely on not even the edge data center, but somewhere close to you. Okay, so that's why people keep demanding for the large computing resources in the local. That's another issue. And some other examples like you have a large concert which you're trying to offer the AR VR capability to every single one. They have Google, they have goggles, they have to watch the show. If you simply calculate how much bandwidth you use to serve like 60,000 people, you immediately realize you will not be able to handle this by using this edge data center. So all this scenario require us to optimize everything, not just the local, but also the coordination between the edge device, the edge data center, and the cloud by considering both computing and the communication between them, especially minimize the redundant computation, the data transmissions from the first. So that is the meaning of this word. So don't get me wrong, I'm not saying we can only optimize or we should only optimize edge devices. What I'm saying is we need to optimize everything, every component, because to squeeze every single components in the whole system to make sure we can keep pushing the boundaries of this computing system. Yeah, sure. Yeah, please.